All right, we have another example here regarding stress and strain. It says a 100-foot long steel wire has a cross-sectional area of 0.0144 square inches. When a force of 270 pounds is applied to the wire, its length increases by 0.75 inches. Determine the stress, determine the strain, and determine the modulus of elasticity of the steel. Okay, so right here by looking at this, I'm going to identify three equations before I even look at the info. It requires me to calculate stress, and I know that stress is equal to force divided by area. So stress is force over area. So here's my stress equation. So again, go look at your engineering formula sheet and see if you can identify that equation. Strain is equal to the elongation, which we use lowercase delta, which is like that funky looking d, over the original length, L0. Okay, I have the original length, 100-foot long steel wire, and I have the deflection, or elongation in this case, 0.75 inches. So I have, check, I have both of those pieces of info. Okay, and then the modulus of elasticity of the steel is what we're asked for. Modulus of elasticity, capital E. And this E for strain is the epsilon, actually. Modulus of elasticity is equal to, guess what? It's easy. Stress over strain. So once you work out parts A and B, here in this problem, you can substitute those pieces of info to solve for C. So let's start with part A, which asks us for the stress. So stress is force over area. Okay, so 275 pounds is applied to the wire. So let me draw this out. I have a wire, drawn over here on the right. Okay, so I have this wire, and it says it's being a force of 275 pounds is applied to the wire. Okay, so I'm going to assume that since it's elongating, that it's a tensile force. So I'm going to go ahead and draw my arrows outward to show that this is being stretched. Okay, so I'll call this F, and that force I know is 270 pounds. Okay, so stress is equal to 270 pounds divided by, and here they were nice enough to give us the cross-sectional area. Cross-sectional area, so again, if you were to go and slice this rod and look at it straight on, you would see a circle. And that would be what shape the cross-section takes, is a circle. I know the area of a circle is pi r squared, so if they didn't give you the cross-sectional area, you could solve for it using pi r squared. Okay, but lucky for us, they told us what it is. In this case, it's 0.0144 square inches. So, stress is equal to, go ahead and take out your calculator and work this out. So I'll go ahead and give you a minute to try that. And by a minute, I mean a few seconds. Shouldn't take you that long. You have it? All right, it should be 18,000. Ooh, that's a big 8. 750. And again, look at my units here. Pounds per square inch or PSI. Okay, so that's how much stress this steel wire is experiencing because of this force that's stretching it. So on every square inch of material, it feels 18,750 pounds, which is quite a lot. Okay, we actually don't even have a square inch of material, but you know, that's what the stress is. So now let's calculate strain. So here's part B. It says strain is equal to the elongation over the original length. So again, identify this formula in your formula chart, okay, in the engineering equation sheet. If you need to, pause this video so you can go ahead and find it and identify what these variables are. And if you do so, you'll find that the numerator is elongation or displacement, and the denominator is the original length. So we're told in the problem itself that the elongation is 0.75 inches. So that's going to go in my numerator, 0.75 inches. And in my denominator, the original length, it's 100 feet. Okay, well, we have to be careful here because I do not want to mix my units. Okay, I need to make sure that I have inches to inches or feet to feet. So 100 feet would be 100 times 12 inches. Okay, so putting that in my calculator, you would find that your strain is equal to 0.000625. Now strain is actually unitless, inch per inch. But to show that it's a strain calculation, we typically leave it as inch per inch, even though mathematically inch over inch is equal to 1. Okay? The last part is calculating modulus of elasticity. If you recall from when we did beam deflection, modulus of elasticity is an inherent property of a material based on its chemical makeup, its resistance to deformation. So that's what we're calculating here, is the modulus of elasticity for this steel rod. So all I need to do is, if I look at my equations, take the stress and divide it by the strain. So 18,750 psi calculated from part A, divided by the strain, which is 0.000625. And remember, this is inch per inch, or 1. So my final answer should be, that's correct, you guessed it, PSI. So let me go ahead and work this out. You do the same, open up your calculator and go ahead and punch these values in. And you should get a large number. It looks like it's 30 million, or 30 times 10 to the 6 psi, which is a very common modulus of elasticity for steel. Steel is incredibly strong. Okay, when we did that beam deflection activity for wood, that wood beam that we used, we got, I think, 1.4 million psi. Here we're at 30, so almost 30 times as strong compared to that piece of wood. Okay, so here's your example of stress and strain, also calculating modulus of elasticity. Thank you for watching.